Hi, I am Karen Braganza. In addition to working at Astronomer, I also contribute to the OSS Airflow project. Today, I will be speaking on the very underutilized cluster policies and how you can use them to implement airflow governance, administration. And just to be clear, this is an airflow-specific concept. It is not based on Kubernetes clusters. Okay, so let's start with a quick introduction to cluster policies. These are defined as Python functions and are very useful for administrators to check and mutate certain Airflow objects. So as an administrator, you might want to enforce certain standards for your DAG authors or Airflow users. For example, maybe you don't want them to enable catch-up for DAGs unless they have max active runs set to 1. Or maybe you want them to offload tasks that do not consume a lot of resources to a lightweight worker queue in order to save costs. Or maybe you want DAG authors to include their emails in the DAG tags so you know whom to contact if you have questions or you need any changes made. In this talk, we will go over such scenarios and talk about how you can use cluster policies to implement solutions for them. So even if you are an Airflow user, not an administrator, it would be helpful to understand how cluster policies work, especially if your admin uses them, so you know what kind of impact it can have on your DAGs and tasks. Additionally, if there are certain configurations that you want applied broadly to many different DAGs or tasks, instead of modifying this in multiple DAG files with the same repeated code, you could just modify it in one place using cluster policies and apply it broadly. So as mentioned before, cluster policies can be used to check or mutate different Airflow objects. And depending on the type of object they modify, there's 4 types of cluster policies. We have DAG policies, task instance mutation hook, and pod mutation hook. So we will go over each of these types and discuss scenarios where each of these can be used. So first we have DAG policies, which are applied to DAG objects when they're loaded in the DAG bag. And these can be used to check and mutate parameters that are in the DAG definition. So these are some governance use cases. You could enforce a DAG ID naming convention. You could require DAG authors to have a DAG description, tags, owner links. You could also add a DAG run timeout to DAGs that do not have one by default. And overall, you can check DAG attributes for certain conditions. And if those conditions are not met, you could either mutate the attributes or you could raise an Airflow cluster policy violation exception, which will result in an import error for the DAG that is violating the policy. So this is what that would look like on Airflow 3, the import error. And this is it on Airflow 2. So let's consider a specific example. I briefly mentioned a scenario where you might want max active runs set to 1 if you have catch-up enabled. Maybe there have been several incidents on your Airflow instance where a DAG author has set catch-up to true. And this is for a new DAG without max active run set to 1. And it has a start date that's very much in the past. This will, when this new DAG is deployed, this will result in several runs of the DAG happening at the same time and consuming a lot of your resources. And if this happens at a critical time when you have a lot of different production pipelines running, those pipelines could fail due to lack of resources. So if you want to implement guardrails that prevents that from happening, you could use the cluster policy like the one I have defined here. So in this case, if catch-up is set to true and max active runs is not 1, it raises an Airflow cluster policy violation exception. And when the DAG author sees this on the UI, they will know that they either need to change catch-up or they need to change max active runs. And you can always make exceptions as well in your function, like I've done here. I have a list of allowed DAGs. So let's say you have a DAG author that wants to deploy a new DAG, and they want catch-up enabled, but they want multiple runs to happen. And they agree to do this at a time when there's not a lot of other DAGs running. you can make an exception for their DAG in the logic of the function as well. So this is another example of using a DAG policy to ensure that all DAGs have an email attached in the tags, so you know whom to contact if there is an issue. This policy checks the tags defined, and it also ensures that there's a valid email in the tags. And if one of these conditions is not met, again, an Airflow cluster policy violation exception will be raised, resulting in an import error. So some things that you need to keep in mind: you could check the DAG definition class in the OSS source code to understand which parameters can be mutated or checked. And there are certain exceptions that need to be considered. For example, frozen attributes like schedule cannot be mutated, but they can be checked within the DAG policy function. Also, task level parameters cannot be mutated through default args in a DAG policy. So we previously talked about applying cluster policies at the DAG level. You can do the same at the task level using task policies. Task policies are applied to a base operator task object to check or mutate its parameters when it is loaded in the DAG bag. And although the policy function requires a base operator object to be passed, you can add conditions within the policy to apply it to a specific class of an operator. So, and also note that these task policies will apply to every task instance of the task. So these are some use cases. You could set failure callbacks or any types of callbacks to tasks that do not have one. You could route certain tasks to specific worker queues. For example, if you have non-critical tasks with many retries, you could route them to a worker queue that uses spot instances to save costs. And on the other hand, if you have certain critical tasks, you could route them to a high priority worker queue. Another use case is you could ban the usage of certain operators, or you could set an executor config for tasks that do not have one. So let's look at some specific scenarios again for this. Let's say you have a database that has critical data that must not be read or modified by any DAGs, unless the DAG author has permission from the administrator to do so. So you could use the task policy like the one I have defined here to check whether the connection created for accessing that database, in this case, it's the restricted Postgres connection, whether that's being used in any of the tasks. And if it is being used, once again, you could raise an Airflow cluster policy violation exception. And if it belongs to the list of allowed DAGs, you could make an exception for it. You wouldn't raise the exception in that case. And here's another example. Certain types of tasks like deferrable tasks usually do not consume a lot of worker resources because they get offloaded onto a triggerer, which does the polling until the condition is met. And also Kubernetes pod operator tasks do not heavily consume Airflow worker resources because the Airflow worker just has to make a call to the Kubernetes API to spin up the pod, and then it has to monitor the pod, stream the logs, which is usually not resource intensive. So as an administrator, you could identify such tasks that are not resource intensive and route them to a lightweight worker queue using task policies to save operational costs. So in this case, I check whether the class path for the task object matches that of the Kubernetes pod operator class path, and also whether the task has a deferrable attribute. And if either of these conditions are met, I route the task to the lightweight worker queue. So some things to consider when creating a task policy: you need to ensure that the attribute being mutated actually exists for the operator in order to avoid an error. And also some of the attributes for dynamically mapped tasks are set as read-only properties, which cannot be directly mutated. Instead, you would have to mutate the partial quarks dictionary. And I'm not going to get into the details of that, but if you want more information on that, this is discussed in some Airflow GitHub issues that you can refer to. Also, to determine which attributes can be modified, you could refer to the base operator class or whichever operator class you want to mutate. So we previously talked about task policies, which would impact every task instance of a task object. If you want to selectively mutate only some task instances, you could use a task instance mutation hook to do that. In a normal task lifecycle, it is first applied when the task instance is created and initialized on the scheduler, and also after the task instance has landed on a worker for execution. This behavior has actually changed on Airflow 3. I believe the task instance mutation hook is no longer applied again when it lands on the worker, only on the scheduler. So generally, these can be used to mutate task instances depending on the try number, map index, runs, etc. Let's go over some specific code examples. Maybe as an admin, you want to remove success callbacks for manual or backfill runs to avoid getting notification spams. So in the first example, I check whether the run ID has the term manual or backfill in it. And if either of these are true, then I remove the success callback by changing it to none. This example actually does not work on Airflow 3 because of the change behavior that I briefly mentioned before. Let's also consider another example where you may want to reroute dynamically mapped tasks to a separate worker queue to avoid overloading your default worker queue. But maybe you only want to do that if there's more than 5 map tasks. So you could check the map index of the task using the hook in the second example. And if it exceeds the threshold of 5, you could route it to the spare high resource worker queue, like I've done there. Something to note, there are some very weird limitations with task instance mutation hooks. Checking or mutating certain attributes may result in an error which will prevent the task instance from running successfully. This is because of the way the task instance mutation hook is applied. Some attributes may not yet be initialized when it is first applied upon task instance creation. And I'm not going to get into too much detail about it since it's beyond the scope of this talk. But if you decide to implement such hooks and you run into any issues with it, you could get a better understanding of this limitation by reviewing the OSS code where the hook is applied in the task instance class. And here's an example that doesn't work. Assigning manual or backfill runs to a specific queue is not going to work because of this limitation. And here's another example that works. Maybe the users want retry callbacks, but only for the second to last task. And especially if there's several tries. So this would allow them to evaluate the issue and fix it before the final try, or maybe this notifies them in time to observe the final try and troubleshoot it live. So this can be achieved by checking the try number, and if it matches the max tries attribute, then a retry callback is added, like in this case. So the user can take action before the final try. So now if you want to go beyond mutating a task instance, if you want to mutate the pod that executes the task code, you could do that using the pod mutation hook. This will modify either the worker pod with Kubernetes executor or the Kubernetes pod operator pod if you're using that operator. So for a Kubernetes pod operator pod, this hook is applied when the worker builds the pod. And for Kubernetes executor worker pod, this is applied when the code to spin up the pod is run on the executor. So here are some governance use cases. You could add init or sidecar containers for logging or metrics collection. You could use this to schedule the pod on a specific node using node selectors. You could protect critical pods from eviction using annotations, add default pod resources, also reset the resources if they exceed a maximum allowed value, or you could add a termination grace period for the pod. And all of these can be applied by modifying the attributes of a V1 pod object. So here's an example of adding a toleration to your pod. Let's say you want your Kubernetes executor worker pods to be scheduled on nodes with the Airflow worker taint. The code in this pod mutation hook function can be used to do that. So now that we have reviewed the different types of cluster policies, let's go over some considerations that you would have to think about when implementing them. So first is that mutations introduced through cluster policies lack visibility. So users may not understand why the attributes that they have set are changing, or why their task instance is not behaving as they expect them to. So they might spend a lot of time troubleshooting this unless the use of the cluster policy is clearly communicated to them. One thing you could do is, instead of silently mutating attributes, you could raise an Airflow cluster policy violation. So it's the user themselves that makes the change and they know about it. In this example, you can see that the user has set their task to run on the default queue. But if you look at the UI, it's actually run on the lightweight worker queue. And this could be very confusing to a user that doesn't know about the cluster policies, because the UI does not make it obvious that this happened because of cluster policies. There's no indication of that. One more thing to note is that code in cluster policies runs on critical Airflow components like the scheduler. So bad code could result in scheduling delays and affect the entire Airflow instance. So any kind of blocking code, such as calls to APIs, must be avoided, and thorough testing is recommended. In this example on my screen, I introduced a simple time.sleep in my task instance mutation hook, and I also included a logging statement so we can track this within the scheduler logs. Next, I triggered a DAG run and observed the scheduler logs, and I saw the logging statement that I introduced, which says sleeping for 600 seconds. And then the scheduler was just hung on that for the next 5 minutes until it was terminated, I think because it wasn't heart beating. So definitely be careful about the kind of code that you introduce. And I believe it's only the task instance mutation hook, though, that affects the scheduler. The others affect different components. So lastly, let's quickly review how these can be implemented. Cluster policies can be implemented in an Airflow local settings file, or by creating a custom module with Pluggy. With Astro, only the second option can be used. And I'm not going to get into the details of implementation because it's beyond the scope of this talk, but we have a lot of documentation, official OSS documentation, and also astronomer documentation that goes into the details of that. Yep, that's it. Any questions?